All right, today we're going to talk about something pretty incredible. How do you turn simple, fine dust into parts strong enough to go inside a jet engine? Well, that's the magic of ceramic casting. It's this amazing process of taking a fine powder and giving it a super precise, high-performance shape. And you know, this stuff is everywhere. I mean, from the phone in your pocket to probes exploring deep space. So how exactly does it work? Let's get into it.
Just look at that. It's a pretty stunning transformation, right? We start with a material that has literally no shape at all, a powder as fine as flour, and we end up with these incredibly strong, complex components that can handle brutal heat and really harsh environments. This isn't just about pouring something into a mold. Nope. It's a really delicate dance of chemistry and physics, and it is a cornerstone of how we make things today.
And that, right there, brings us to the core problem. See, you can't just melt and pour ceramic powder like you would a metal, and you can't just press it into a mold like you would a plastic. It just doesn't want to cooperate. So the big question is, how do you convince this really stubborn powder to form into the intricate, precise shapes that we need? That's the puzzle we're going to solve.
We're going to explore 3 brilliant ways to solve this problem. We'll kick things off with the classic, almost artistic method of slip casting. Then we'll shift gears to its high-speed industrial cousin, pressure casting. From there, we'll look at something totally different, tape casting, which makes a whole new form factor. And then we'll wrap it all up by digging into the science that makes all of them tick, mastering that liquid mix and controlling the process to get it just right.
Okay, so first up is slip casting. This is one of the oldest, most elegant methods out there. It's the absolute go-to technique when you need to make really intricate or even hollow shapes. Think of a delicate teacup or a complex turbine blade, things that would be pretty much impossible to make any other way. The genius of this whole thing is really its simplicity. You've got 2 main players here. On the left, you've got the slip, that's just our ceramic powder mixed up in water to make a slurry, and on the right, you have the plaster mold. Now the key is that the mold is porous, kind of like a superfine sponge. The magic trick is something called capillary action. The plaster is basically thirsty for the water in the slip, so it literally sucks it right out, leaving a solid layer of ceramic particles packed nice and tight against the wall of the mold.
So let's just walk through it real quick. First, you pour that liquid slip into the mold. As that plaster mold starts pulling the water out, a solid ceramic wall begins to build up, growing from the outside in. The longer you let it sit, the thicker that wall gets. If you want a hollow part, you just pour out the extra liquid slip from the middle. Easy enough. And once it's firm enough to handle, you just open the mold and carefully take out your brand new part.
Okay, so this part you've just pulled out of the mold, it has a special name. It's called a green body. Now, it's not actually green, of course. Green here just means it's unfired, kind of like green wood that hasn't been seasoned. It has the exact shape you want, but here's the catch. It is so fragile. Think about a piece of chalk. That's about how strong it is. It's really just powder being held together by a little bit of binder. This green body is such a critical step, and you have to be so careful with it, because the real, almost superhuman strength, that only comes after it gets fired in a super hot kiln.
All right, so slip casting is elegant, for sure, but that gentle capillary action, it's slow. So what if you don't need just one perfect vase, but you need, say, 10,000 identical sinks every single day? For that, you got to speed things up, and that's where pressure casting comes into play. You can think of it as the industrial evolution of slip casting, built for speed and massive scale. The key difference here is the force that's driving the process. Slip casting relies on that gentle, natural pull from the mold. Pressure casting, on the other hand, just supercharges the whole thing. It applies high external pressure to the slip, which actively forces the water into the pores of the mold. This speeds up the dewatering process like you wouldn't believe, shrinking a casting time that could take hours down to just a few minutes. It's all about trading that patience for raw power.
Okay, so we've made complex 3D shapes both slowly and quickly. But what if you need to solve a totally different problem? What if you need to make something that's incredibly thin, perfectly flat, and maybe as large as a sheet of paper? Well, for that, you need a completely different way of thinking. You need tape casting.
And this right here is the heart of the operation. You pour your ceramic slip onto a moving plastic carrier film. That film then slides under what's called a doctor blade, and you can think of it like a perfectly calibrated high-tech squeegee. The blade is set to a super precise height, and it smooths the slip into this flawless, uniform layer, a tape, with a thickness controlled down to a few microns. It's just a beautifully precise and continuous process.
So why go through all this trouble just for a thin sheet? Because, and this is no exaggeration, modern electronics would not exist without it. These ceramic tapes become the substrates for complex circuit boards. They're amazing at getting rid of heat while insulating all the electricity. They get layered, sometimes by the hundreds, to create the tiny little multi-layer ceramic capacitors that are in, well, literally every single electronic device you own. Tape casting is building the invisible foundation of our digital world.
So, we've looked at 3 really different methods for shaping the unshapeable. But here's the thing. It doesn't matter if you're using gentle suction, high pressure, or a Dr. blade. Your part is going to fail if you don't get the science right. The ultimate success for any of these methods boils down to just 2 things: the formulation of your slurry and the precision of your process control. This is where it all comes together.
And this table gives us a great little summary of the playing field. Slip casting is what you choose for low-volume, complex, artistic-type pieces. Pressure casting takes on similar shapes, but cranks up the volume for industrial production. And then tape casting just carves out its own special niche, creating huge volumes of a totally different form, those ultra-thin sheets. And of course, each one of these methods places unique demands on the mix.
So what's actually in this magic liquid, this slurry? Well, obviously, you start with your ceramic powder and a liquid, usually just water. But if you just mix those 2 things together, you get useless sludge. It's not going to work. The real secret sauce starts with adding something called a dispersant. This is awesome. Think of it like a chemical that puts a force field around every single particle, like a little personal space bubble. It makes them all repel each other, which is what allows the slip to flow so smoothly. Then you've got to add a binder. That's basically the temporary glue that holds the whole fragile green body together so you can actually handle it. And finally, a plasticizer, which makes that glue a little more flexible so the part doesn't just crack as it dries.
When you get that recipe absolutely perfect, this is what you're aiming for on a microscopic level. It's a dense, perfectly uniform structure. You see how every particle is nestled tightly against its neighbors? There are no gaps, no clumps. This ideal packing is what guarantees that the final fired part will be super strong and completely free of flaws. It all starts right here. But when your formulation or your process is even a little bit off, you get this. And this is a total nightmare for a ceramics engineer. This is a defect called a pipe void. It happens when a little pocket of slip gets trapped inside the part as it's forming. As the mold keeps pulling water from that isolated pocket, the slurry literally rips itself apart, creating a hidden internal crack that can lead to a catastrophic failure down the line.
And yeah, pipe voids are just one of the enemies you're fighting. You can get lamination, where layers peel apart, which is a sure sign the slip was stressed as it filled the mold. Drying cracks pop up when one part of the green body shrinks faster than another. Warpage is when the part twists out of shape because of uneven density. Pinholes, those are the little ghosts of trapped air bubbles you didn't get out. And sedimentation, where heavy particles sink to the bottom, that tells you your suspension wasn't stable. You see, every single defect is a clue that points right back to a problem in your mix or your process.
And believe me, these variables have a huge, measurable impact. Just take a look at this chart. It shows how something as simple as the dampness of the plaster mold affects the strength of that fragile green body. A mold that's too dry, what we call low consistency, sucks water out way too aggressively. That messes up the perfect particle packing and gives you a weak part. A slightly wetter, higher consistency mold pulls the water out more gently, allowing the particles to settle into a much stronger arrangement. It is an incredibly delicate balance.
So to manage this balance, engineers have a whole dashboard of controls they can use. They can fine-tune the slip's viscosity and something called its thixotropy, which is a cool property where a fluid gets thinner when you stir it, kind of like ketchup. That helps it flow into the mold but then stay put. They control the temperature, the pressure, the exact amount of time the slip spends in the mold, even the permeability of the mold itself. Every single one of those levers has to be in the perfect position.
So in the end, all of these techniques, they're really about one thing: transforming an inert powder into incredible performance. It's a foundational technology that is quietly enabling our entire modern world. And that leaves us with a final question to think about. As we push for breakthroughs in things like solid-state batteries, personalized medical implants, or more efficient electronics, what other future innovations are just waiting to be unlocked by someone who can truly master the delicate science of the mix?